So hey friends, we are going to revise surface chemistry. So let's get started. Surface chemistry. Surface chemistry deals with phenomena that occurs at the surface or interfaces. The accumulation of molecular species at the surface rather than in bulk of a solid or liquid is termed as adsorption. The molecular species of substances which concentrate or accumulates at the surface is termed as adsorbate, and the material on the surface of which the adsorption takes place is called adsorbent. The process of removing an adsorbed substance from the surface is called desorption. Distinction between adsorption and absorption. Adsorption, it is a surface phenomena that is, it occurs only at the surface of the adsorbent. In this phenomena, the concentration of the surface of the adsorbent is different from that in the bulk. Its rate is high in the beginning and then decreases till equilibrium is attained. And in absorption, it is a bulk phenomena that occurs throughout the body of the material. In this phenomena, the concentration is same throughout the material. Its rate remains same throughout the process. Cause of adsorption. Unbalanced or residual attractive forces of the adsorbent are responsible for attracting the adsorbate particles on its surface. Enthalpy and entropy change during adsorption. Adsorption is an exothermic process, that is delta H is negative, and as molecules are held on the surface, entropy decreases, that is delta S decreases. Delta S is negative and delta H is also negative. Exothermic and entropy decreases. Adsorption is a spontaneous process. Delta G is also negative, which is possible only if delta H has sufficiently high negative value. Hence, delta G, delta H and delta S all are negative. Delta G, delta H and delta S all are negative in adsorption phenomena. Or in surface chemistry, delta G, delta H and delta S are all negative. Since delta G equal to delta H minus T delta S. Comparison of physisorption and chemisorption. Physisorption, it arises because of van der Waals forces. It is not specific in nature. It is reversible in nature. It depends on nature of gas. More easily liquefiable gases are adsorbed easily. Enthalpy of adsorption is low, 20 to 40 kJ per mole. Low temperature is favorable for adsorption. It decreases with increase of temperature. No appreciable activation energy is needed. It depends on the surface area. It increases with an increase of surface area. It results into multimolecular layer on adsorbent under surface under high pressure. Not specific, reversible, low temperature, no appreciable activation energy, and multimolecular layer. You can learn it by Prime Minister. PM. Physisorption, multimolecular layer. Okay. Now we will see chemisorption. It is caused by chemical bond formation. It is highly specific in nature. It is irreversible. It also depends on the nature of gas. The gases which can react with the adsorbent shows chemisorption. Enthalpy of adsorption is high, 80 to 240 kJ per mole. High temperature is favorable for adsorption. It increases with increase of temperature. High activation energy is sometimes needed. It also depends on the surface area. It too increases with an increase of surface area. It results into unimolecular layer. CU, Chandigarh University, you can learn it by chemisorption unimolecular. Okay. And physisorption multimolecular, Prime Minister PM. Freundlich adsorption isotherm. X upon m equal to kp to the power 1 upon n, where n greater than 1. Log x upon m equal to log k plus 1 upon n log p, where x is the mass of the gas adsorbed on mass m of adsorbent at pressure p. K and N are constant, which depend on the nature of the adsorbent and the gas at particular temperature. Okay, slope is 1 upon n and intercept is log k when the graph is made between log x upon m and log b. Similarly, for adsorption of solute from solutions, x upon m equal to k c to the power 1 upon n, where c is the equilibrium constant concentration. That is when adsorption is complete. Log x upon m equal to log k plus 1 upon n log c. Plot of log x upon m versus log c is linear. Factors affecting adsorption of gases by solids. Nature of gas being adsorbed. Gases with higher critical temperature are easily adsorbed. Since critical temperature 8A upon 27B square, temperature above which gas cannot be liquefiable is critical temperature. Nature and surface area of adsorbent. Greater the surface area, greater is the adsorption. Pressure at constant temperature, the adsorption increases with increase of pressure. Temperature at adsorption is an exothermic process. By applying Le Chatelier's principle, increase of temperature decreases the adsorption and vice versa. Catalysis. Substances which accelerate the rate of chemical reaction and themselves remains chemically and quantitatively unchanged after the reactions are known as catalyst, and the phenomena is known as catalysis. Catalysts can be broadly divided into two groups: homogeneous catalysis and heterogeneous catalysis. Homogeneous catalysis is the process in which the reactants and the catalyst are in same phase, and in heterogeneous catalysis is the process in which reactants and the catalyst are in different phases. Important features of solid catalysis. Activity. The activity of a catalyst is its capacity to increase the speed of the chemical reaction. Activity. The activity of a catalyst is its capacity to increase the speed of the chemical reaction. Selectivity. The selectivity of a catalyst is its ability to direct a reaction to yield a particular product. The catalytic reaction depends on the pore structure of the catalyst, and the size of the reactant and product molecules is called safe selective catalysis. Zeolites are good safe selective catalysts because of their honeycomb-like structure, ZSM5. Zeolite sieve of molecular porosity. 5. Enzyme catalysis. Enzymes, also called biochemical catalysts, as are complex nitrogenous organic compounds, proteins, which are produced by living plants and animals. Enzymes are highly efficient, specific, and are active at optimum temperature range of 298 to 310 K and pH range of 5 to 7. A colloid is a heterogeneous system in which one substance dispersed phase is dispersed as very fine particles in another substance called dispersion medium. The range of diameters of colloidal particles is between 1 and 1000 nanometer, 10 to the power minus 9 to 10 to the power minus 6 meter. Classification of colloids based on physical state of dispersed phase and dispersion medium. Dispersed phase and dispersion medium, types of colloids and example: solid, solid, some colored glasses and gemstones, sol, paints, cell fluids, aerosol, smoke and dust. Sol is solid in liquid, aerosol is solid in gas. Gel is liquid in solid, cheese, butter and jellies. Emulsion is liquid in liquid, milk, hair, cream. Oil in water and water in oil. Oil in water is example is milk, and water in oil like Nivea cream. Aerosol, liquid in gas. For aerosol, fog, mist, cloud, insecticide sprays. Solid sol, gas in solid. Pumic stone, foam, rubber, foam, gas in liquid. Froth, whipped cream, soap and leather. Classification based on nature of interactions between dispersed phase and dispersion medium. Lyophilic colloids, also called as reversible sols, are directly formed by mixing substances like gums, gelatin, starch, or rubber with a suitable liquid, the dispersion medium, and are quite stable. Lyophobic sols. Lyophobic sols are also called irreversible sols and can be prepared only by special methods and are not stable. Classification based on type of particles of the dispersed phase. Multimolecular colloids. Colloid particles are aggregates of molecules, S8 or gold. Multimolecular colloid, macromolecular colloid, and associated colloid. So multimolecular colloidal particles are aggregate of molecules S8 and gold, and macromolecular colloids. Colloid particles are macromolecules, starch, cellulose, protein, etc. Associated colloids, micelles. These are formed by electrolytes like soap and detergents above a particular concentration 10 to the power minus 4 to 10 to the power minus 3 called critical micelle concentration CMC, and above a particular temperature called Kraft temperature. Usually ions aggregate to form micelles. Above a particular temperature called Kraft temperature and above a particular concentration called critical micelle concentration. Preparation of colloids. Usually ions aggregate to form micelles. Preparation of colloids by chemical methods such as double decomposition, oxidation, reduction, or hydrolysis. By electrical disintegration or Bredig arc method, which involves dispersion as well as condensation. Colloid sols of gold, silver, platinum can be prepared by this method. Gold, silver, platinum, Bredig arc method. By peptidization, which is the process of converting a precipitate into colloid. So by shaking it with dispersion medium in the presence of a small amount of electrolyte. The electrolyte used for this purpose is called peptidizing agent. Purification of colloidal solutions. Dialysis, electrodialysis, ultrafiltration. Dialysis is the process of removing a dissolved substance from a colloidal solution by means of diffusion through a suitable membrane. Electrodialysis, dialysis of impure colloidal solution of an electrolyte in presence of electric fields. Ultrafiltration, it is the process of separating the colloidal particles from the solvent and soluble solutes present in the colloidal solution by specially prepared filters which are permeable to all substances except the colloidal particles. Ultrafiltration, it is the process of separating the colloidal particles from the solvent and soluble solutes present in the colloidal solution by specially prepared filters which are permeable to all substances except the colloidal particles. CMC for soaps is 10 to the power minus 4 to 10 to the power minus 3 mole per liter. Zeta potential or electrophoretic potential AgI / I minus K plus. I minus is fixed layer and K plus is mobile layer or diffuse layer. I will explain it later. Properties of colloidal solution. Colligative properties, Tyndall effect, Brownian movement, charge on colloidal particles, electrophoresis, electrical property, and Tyndall effect is optical property. Properties of colloidal solutions. Colligative properties. Colloids show colligative properties like relative lowering of vapor pressure, elevation of boiling point, etc. and magnitude of colligative properties of colloid is much less than true solutions due to large size of colloidal particles. Tyndall effect. Optical activity. Scattering of light by colloidal particles due to which the path of light beam become visible. Brownian movement. Mechanical property. Zigzag movement of colloidal particles due to unbalanced bombardment by the molecules of dispersion medium. Charge on colloidal particles. Colloidal particles always carry an electric charge and nature of charge positive or negative is same on all the particles in a given colloidal solution. The charge is due to preferential adsorption of the ions from solution. Electrophoresis is electrical property, movement of colloid particles towards one of the electron on passage of electricity through colloidal solution. The direction depends on the type of charge on colloidal particle. So there are three. Tyndall effect is optical property, and Brownian movement is mechanical property, and electrophoresis is electrical property. Okay, so three. Coagulation of colloids. Precipitation of colloidal solution by induced aggregation of colloidal particles. Lyophobic sols can be coagulated by electrophoresis, boiling, persistent dialysis, mixing of oppositively charged sols, and addition of electrolytes. Hardy-Sulz rule. In case of electrolytes, the ion carrying charge opposite to that of the colloidal particle is effective in causing coagulation, and greater the valency of an ion causing coagulation, greater is the coagulation power or coagulation power. Coagulation power is inversely proportional to the coagulation value, and they have given a question on it. They have put the values and you have to arrange them in increasing of the order of their coagulation power, as coagulation power is inversely proportional to the coagulation value. So those which are having a higher coagulation value will be having lower coagulation power. The minimum concentration of electrolytes in millimoles per liter required to cause precipitation of a sol in 2 hours is called coagulation value. Millimoles per liter. The smaller the quantity needed, the higher will be the coagulation power of an ion. Lyophilic sols can be coagulated by adding of electrolyte and addition of a suitable solvent. Protection of colloids. When a lyophilic sol is added to the lyophobic sol, the lyophilic particles form a layer around a lyophobic particle and thus protect the latter from electrolysis. Lyophilic colloids used for this purpose are known as protective colloids. Lyophilic colloids act as protective colloids. The minimum mass of protective colloids in milligrams that must be added to 10 ml of standard red gold sol so that no coagulation occurs when 1 ml of 10% NaCl solution is repeatedly added to it, called the gold number of a lyophilic colloid. Gold number is defined for lyophilic colloid which act as protective colloid. Smaller the gold number of a protective colloid, greater is its protective action. Gold number inversely proportional to the protection. Emulsion. Colloid in which both dispersed phase and dispersion medium are in liquid state. Types of emulsion. Oil in water, where dispersed phase is oil and dispersion medium is water. Milk, body lotion, and water in oil, where dispersed phase is water and dispersing medium is oil. Butter, cold cream. Emulsification, process of making an emulsion. Emulsifying agent used to stabilize the emulsion. Example, soaps and detergents are emulsifying agents. Demulsification, separating the two components of an emulsion. Methods used are boiling, freezing, changing pH. Application of colloids. Blue color of the sky is due to the scattering of light by dust particles. Artificial rain can be caused by throwing electrified sand on spraying a sol carrying charge opposite to one on clouds from an aeroplane. Blood is a colloidal solution of an albuminoid substance, and the styptic action of alum and ferric chloride solution is due to coagulation of blood, forming a clot which further stops further bleeding. Formation of delta is due to coagulation of colloidal solution of clay, river water by electrolytes present in the sea water. Electrical precipitation of smoke. Quaternion precipitated by coagulation the carbon particles of the smoke on metal plates connected to source of high potential before allowing to pass through the chimney. Purification of drinking water by adding alum to coagulate the suspended impurities. So this was all about surface chemistry, and you have to focus on Hardy-Searle rule and disperse phase, dispersion medium, and the properties of colloidal solutions. Okay, and here protective colloid is formed by lyophilic colloids, and the the minimum mass of the in milligrams of the lyophilic colloid must be added to 10 ml of standard red sole so that no coagulation occurs. When 1 ml of 10% NaCl solution is rapidly added to it, called the Gould number of the lyophilic colloid, protective colloid. Okay, so all the best.